Next talk is from Caroline Lima, also from University of Waterloo, and she will be speaking about harvesting entanglement from fermionic fields with linearly coupled detectors. And the floor is yours. You'll have 12 minutes, and I'll give you a 2-minute warning before the end.
Thanks, Adam, for the introduction. As he said, I'm Caroline Lima, and I'm going to present the work that I did as master's students here when I was a Perimeter Scholars International Scholar, and in collaboration with Rick Persh and Eduardo Martinez. Since I'm talking about entanglement harvesting, it might be useful to just review briefly what is entanglement harvesting, even though some people have already talked about it, and are going to talk about that tomorrow as well. So we know that space-like separated regions can become entangled via the local interaction with the vacuum of a quantum field. And a possible way to extract that is by coupling in each of this space-time region, one non-relativistic two-level system, quantum system, right? And that's exactly what is shown in this picture. But also they put this mirroring. They are mirrored detectors, so you can see that it's not actually like point-like, and you can also see the light cone here. The motivation for our work was that entanglement harvesting protocols have been investigating in many setups, and we wanted to investigate a little bit more the fermionic fields case. Actually, the previous works in the literature that have investigated the fermionic case were in 1986 Takahi, and more recently Jorma Loco, and also Vladimir Toussaint. They showed that they showed this theorem that basically says that you can that the response of the detector coupled quadratically to a massless direct field can be written as a function times the response function of the detector in the case of the massless scalar field. And this is important because in general, what we had until now in the literature was that quadratic couplings were the ones used. And so this was a way of combining what is more studied, that is the case of UDW detector, which are like real scalar models, and the ones, the more common fermionic ones. I hear someone. Anyways, so the pros of this model is that it's very intuitive. For instance, QED is going to show you a quadratic coupling. And also, if you want to respect U1 symmetry, given that the detector respects U1 symmetry, you also need to couple that to a bosonic operator, right? And so it makes sense to consider the quadratic coupling. It also has some cons. One of them being that it shows too much symmetry between the particle and the antiparticle sectors. So this makes it really hard to design some specific particle physics experiments, like to design, not to design, but to model them. Also, since we know way more, it's well studied in the literature, the UDW detector model, and it has a linear coupling. It's really hard to compare a fermionic quadratic one with a UDW linear one, because you don't know exactly if the different result that you obtain, like what part of this different result comes from the quadratic coupling versus linear, and what part comes from the statistics of the field, right? And these two works by Alexson Sachs, Robert Mann, and Eduardo Martinez, in them they studied a bit more the case of quadratic coupling for bosonic fields, so for scalar fields, and with that, it's you can try to connect a little bit better the two cases, the fermionic quadratic and the scalar quadratic ones. But also in these works, they show that the results have UV divergences that cannot be removed with smearing functions. So now in our work, we use linear coupling. And then you might ask, why linear coupling? So these two works, one by Torres, Perche, Landulfo, and Matzas, and the other one by Perche and Martin Martinez, they showed that actually a linear coupled fermionic particle detector can be physical. And in fact, it describes the emission and absorption of neutrinions by nucleons. So it does make sense to consider this this model for us to then perform the entanglement harvesting protocol. So I will just go through quite fast to the model that they proposed. So here we see the beta decay process. So and in order to model that, we have the Fermi interaction Lagrangian. And here we have the Fermi constant and the fermionic fields, and also the projector of the left-hand component of the spinors. So where the weak interaction takes place. And we need to try to, based on this Lagrangian, find a way to find another Lagrangian that looks more similar to what we are used to in a UDW detector model, right? So they do a lot of manipulations that I don't have enough time to go into much detail now. But basically, they are going to obtain an interaction Hamiltonian weight such that we have, like here, we have the neutrinos as the fermionic, neutrino and antineutrino as the fermionic fields. And the rest of the interaction, so the proton, neutron, and electron, are coming here as an effect, like our model as a two-level quantum system, like we wanted, right? So we have that here, the ladder operators here is going to include the annihilation for the electron, the annihilation for the proton, and the creation for the neutron. And similarly, the lowering operator is going to create an electron, create a proton, and then annihilate the neutron. Also, we have the spinor space-time smearing function that came from the spatial distribution of the electron, neutron, and proton, defined as this. And here in omega, we have actually delta m is the difference of the mass between the neutron mass and the proton mass, and omega e is basically the energy scale for the electron. So we have pretty much everything that we need for the particle detector model, right? So we have the two-level non-relativistic quantum system that I talked about before. It is coupled to a fermionic quantum field, which is the neutrino here. And we have the interaction Hamiltonian weight that we need. Now, I want you to notice that in this model, the ground state and the excited state, they couple to different sectors of the neutrino field. So you can see if you excite, the excitation of the detector is going to happen like here. So when through the emission of a particle or the absorption of an antiparticle, and the de-excitation is going to happen when you emit an antiparticle or absorb a particle. So that's an important feature of this model. Oh, something happened here, but okay. Okay, so finally, for the entanglement harvesting that we are interested in. So the first question that comes to mind is that, can we harvest entanglement from a complex scalar or fermionic vacuum using the linear coupling that we were motivating? The answer is it depends. So if both particle detectors models start in the same state, so both in ground or both in excited states, then we cannot harvest entanglement. And the reason for this is that the field correlations appear only between the particle and the antiparticle sectors. But if we do start the protocol with the two particle detectors in different states, then we can indeed harvest. And that was the case that we investigated a bit further.
2-minute warning.
So, okay.
2-minute warnings.
Thank you. So we performed the calculations for a curved spacetime, but then for explicit examples, we used the Minkowski spacetime. We computed both examples for fermionic and complex scalar models to be able to compare them as well. The two detectors are identical. The coupling constants we also consider identical. Of course, we consider no correlation before the interaction of the field. And this mirror and the switching functions we consider to be Gaussian. And of course, one detector was in the ground and the other one in the excited state, as I said, that this is a condition for us to be able to harvest. Among one of the plots that we did was these ones. So here we are plotting negativity as a function of the detector separation. So the separation in space is given by L, so it's here. And in time is T0, so it's in this direction. And we fixed omega, which is the energy gap of the detector, to be 4 over T. And in this plot, we're considering massless point-like detectors. So you can see that both of them are similar. We do have more oscillations in the case of the fermionic model. And of course, the magnitude is also different. So they do present some similarities, but also some differences. And the conclusions that we have had in our work is that we can only harvest entanglement from fermionic and complex scalar fields using linear couplings when the two detectors start in different states. The complex scalar model grasps most of the features for the fermionic model in certain conditions. One of them that I didn't have time to talk about is that when the mass of the fields is sufficiently large. And if also we did not discuss in this talk because of time constraints, but if you take the detector's mirroring function to be complex, you can also, we show that you can increase the harvested entanglement by up to 2 orders of magnitude. And that was my talk. Thank you for your attention. And do you have any questions?
Thank you, Carolina. Okay, so we'll have time for one question. So, wow, there's a lot, which is really good. But the other ones can go to Slack or afterwards when we finish the session. So actually, like some people gave his stop raising his hand. Okay, so the one that's still there, Robert, you can go ahead asking your question.
Yeah, okay, thank you. It went by a bit fast. So you discussed several couplings. Could you just show me again what the coupling is you're using for the fermionic case, please?
Yeah. So the fermionic case, we are using this coupling. So here you're just using, see that it's linear in the fermionic field, right?
So nu is any fermionic field.
Yeah,
you've got a neutrino there, but that doesn't really matter, right?
Yeah, exactly. Because I just wanted to keep it like the presentation short and motivated using the neutrino field. But indeed, we use a general fermionic field, not necessarily a neutrino field. You're right.
And what is it J/ you've got there for lambda?
We define, I can show you later like a better explanation, more step-by-step explanation of this, but basically this is the hadronic current. I can actually, do we have time, Adam, to go further, or?
I think we should move it to the end of the session.
Yeah, maybe you could put it in the Slack then.
Okay, yeah, I'll do that.
Okay, thank you.
No worries, thank you.
So let's thank Carolina again.